Hello everyone, and let's carry on with this relative motion. And in short, let me recap what we talked this in relative motion that we studied in the previous class. We said that when a velocity of one object with respect to another is given to us, we can always write velocity of one with respect to another minus velocity of two with respect to another. So this is important formula we need to keep in mind. So now in this video we will be learning to use this formula in certain cases. So there are certain types of questions that are very popular based on this formula, and whenever the need will arise, we will be using this formula. So we are starting with this first case or first type of question that includes rain and a man or a person. So how this rain appears to a person, we are going to talk about over here. So rain that falls down with respect to maybe ground is given to you, and a person may be moving. So what that person observes that rain is going to be discussed in this case. So let me first try to connect it with the real life situation. So let's say raindrops are falling. So we can consider one raindrop, because we will be saying all the raindrops will be following the way one is moving. So let's say this is a representative raindrop and it's moving down, maybe it's vertically down. Let's say that's the ground. So this is one case, and if wind is blowing and other steps are also, so this can also be the case, raindrops are following in this way or maybe in another direction. So their directions can be vertically down exactly, or maybe having some component in horizontal direction as well. Okay, so let's say this is the raindrop situation, so we will call it as the velocity of rain. And when we call it as the velocity of rain, basically this is the velocity of rain with respect to ground. So that means with respect to ground, it's falling in this way. And you must have observed, let's say you are seeing this raindrops falling down and you are standing over here. So you'll find the raindrops will appear as it is. That means they are coming vertically downside. But let's say after a certain time you ride on a bike or on a car or start running in this direction. So if you start running in this direction with some velocity, so we'll call it the velocity of man. And I'm not writing this g, that means this is obvious, this is the velocity of man with respect to ground, and this is a ground. And your observation in real life situation must have been so that if you start moving in one direction, maybe running, maybe by a car or a scooty or anything, then you'll find the same raindrop which was coming vertically downside when you were standing will not appear to you to coming vertically downside. And can you think what is the direction, or can you identify what is the direction that you observe? So they will not appear like this. So now raindrop will not appear to this person like this. Rather, they will appear in the direction of the person. It appears like these raindrops are coming towards that person. So whenever you are moving, so raindrops appears to come towards you. More the velocity, you must have observed, if you speed up the scooty or car, then their directions are becoming more almost towards you. And if you further increase it, their raindrops direction will further come towards you. So what angle they make from the vertical, that becomes our concern. And what the velocity that you are watching, that becomes the concern. So what is going to happen? This is the velocity of raindrop. This is the velocity with which you are moving, and whatever the new velocity is coming, that's apparent velocity, or that's a velocity relative to you. That means this is the velocity of raindrop with respect to man. So this is what we need to find. So we need to find the velocity of raindrops with respect to man using this relation. That means using the relation of relative motion. So what the concept goes behind, we need to learn over here, but this is the practical situation that you must have observed in your real life. Or if you haven't observed yet, next time whenever there is a rain and you start let's say traveling by a car, or if you get a chance, then you observe the raindrops coming towards the window or the screen wind of these windscreen of this of the car, then you'll find they will appear coming towards more you as you speed up. Why this happened and how this happened, that's what we're going to talk about here. So let's start with this. So there are going to be few velocities, as I mentioned. One velocity will be velocity of man. This will mean, when I'm going to write like this will mean velocity of man. Simply we can call this. And if we write it properly, so it's with respect to ground. So if nothing is said, so it's with respect to earth or ground. And for us, this ground is stationary. And another term that we are going to use is a velocity VR, capital R for rain. So that's going to be velocity of raindrops. And that's also going to be with respect to ground. So these two numbers will be given to you. But what we need to find, the velocity as seen by that person. So we need to find this thing, velocity of rain as seen by man. So that's going to be velocity of man with respect to, we need to write this as a man. So it's the velocity of rain with respect to man. So how the man observes the rain velocity is going to be our purpose, or that's going to be the thing that to be calculated. So we can follow this rule, and we already got to know what the formula is going to be. Formula is simple. This velocity of rain with respect to man is equal to velocity of rain minus velocity of man. That's all. So the two velocities will be given to you, and the third velocity you need to find. So we need to solve. VR will be given to us, VM will be given to us. So we need to use basically subtraction of two vectors, and using the subtraction of two vectors we can find out what the velocity of raindrops are with respect to person, and that will do our job. Now as we have already talked about how to solve these kind of questions, so better would be that we use this geometric method. So if let's say this is the velocity of raindrop that is given to us, let's say this is the velocity of man that is given to us. We are taking a simple example. So what will be the velocity of man with respect to rain? I'm writing otherwise. We need to find the velocity of rain as seen by the man, because man is going to be observer. And if we need to find this, so what we need to do, first we need to draw this vector. So that's going to be velocity of rain, which is here. So that's going to be this vector, vertically down. In this case I'm considering vertically down, and that becomes the velocity of rain. Then what we need to do, subtract, that means we need to reverse the velocity of man, this vector, we need to reverse it and then add with it. So when we reverse it, it becomes like this. And adding, we need to place the tails together, or we can place head tail as you like, choice is totally yours. So I'm placing the tails together. So this will become VM. I'm writing it as VM. Basically it's a minus VM. So minus is for direction. So direction has been drawn. Hence there's no need to write this minus. And this is simply magnitude. This is simply magnitude. You have gone through the vectors. So what the resultant is going to be. So whatever the resultant is, that's our answer. So that's the resultant. So this vector which I'm drawing now is going to represent the magnitude of velocity of rain as seen by man. So velocity of rain as per the person will not appear vertically down, rather it will appear at a certain angle. What that angle is, this angle is the angle of importance for us. So that's, let's say, alpha. And we can easily find this alpha angle. How we can find this alpha angle? We can say tan alpha is equal to this component of man velocity and this component of rain velocity. So from here we can find out at what angle from the vertical the rain turns for that person. And moreover, we can also find this value. So what this velocity of rain with respect to man is going to be, let me write over here. Velocity of rain with respect to man, this is going to be under root Vm square plus Vr square. I'm not saying use this as a formula, remember this as a formula. What I'm trying to say, that these two numbers are going to give in to you. Then after, use this, draw this velocity, whatever it is given, then reverse it and add them together, find the resultant. No matter it is in what direction and this is in what direction, you can always do this. You can draw this, you can reverse this, you can add the two vectors, you can find the resultant value. That resultant value is going to be magnitude, and the resultant direction is going to be the direction of raindrops. Making sense? So that's the theory behind. Now let's pick a few examples to use this particular point. So let's pick this simple question, and it says rain is falling vertically down, and the velocity of rain is given to us. We need to find the velocity of rain again, but this time with respect to a running man which has a velocity 4 meters per second towards east. So how we are going to solve? We will be simply following the rules that we just learned, and we will draw. This is the velocity of rain or raindrops, we can call that VR, and that is given to us. What is the VR, velocity of rain, as a magnitude? That's a 3 meters per second. We will be using whenever its need arise. So and the next point is given that some person is moving towards east. So first of all, we need to make sure that whether we are writing the directions properly. So this direction we can assume as the east direction, and we are considering this as the east. So this is going to be west, and this is vertically up. That's not north, because we need to see the things here in the 3 dimension. So that's upward direction. So this becomes downward direction. Can you think of? And so where is the north and south? So north will be at 90 degree inside, and south will be at 90 degree in the horizontal direction from this 90 degree in this direction. So that's basically 3-dimensional way we need to think, right? And here it was given towards east, so we need to draw east in this screen. So east can be considered this, and upward will remain upward, downward will remain downward. So north and south, they are not needed, so we can erase them, and we can think of this is the situation that is going on. If this is the situation, so we can say where the velocity of man is towards east. So this is velocity of man, and magnitude of velocity of man is also given to us. So you will write it as velocity of man is equal to 4 meters per second. Now you got to know all the two, but what we need to find is the velocity of rain as per the running man. So let's come to that. So to find the velocity of rain as per the man, what we need to do, we need to say that this is the formula we are using. Velocity of rain with respect to man is going to be velocity of rain minus velocity of man. So subtract the two velocities. Another way for you is to write I cap, j cap and use the vector form, or you can write this subtraction of vector using geometric method. That's what I'm going to use over here. So I will be drawing this velocity of rain as such. So that's a velocity of rain, that is basically value which is 3. And I need to change this, reverse it. So reversing will lead to this, and joining the tails together. So this will be a vector called 4 magnitude. So this is 4 magnitude, that's a 3 magnitude. And this is totally is the velocity of rain as per the man. Now we can find the resultant. They are at 90 degree, the 2 components. So this will be the velocity of man. This is the velocity of rain with respect to man. And we know how much that is going to be. So from here we can have our conclusions that the velocity of rain as seen by the running man is going to be under root 3 square plus 4 square, which is square root of 25. That leads to 5 meters per second. That means that person is going to observe rain with moving with 5 meters per second, which was actually moving with a 3 meters per second. So that's the new value of raindrops. And what this angle is, so this angle is, let's say alpha. We can claim this tan alpha is going to be equal to 4 by 3. So from here we can find this alpha. Alpha is going to be 53 degree. So or we can say simply tan inverse if we are not able to find exactly angle. So tan inverse 4 by 3 or 53 degree. And so how to say what is this angle? So this angle is of raindrops as per the person. So you will say this angle is from the vertical direction towards this direction, and this direction is west direction. So we will say the raindrops are coming like this. That means they are making 53 angle from the downward direction, vertically down direction towards west. So from vertically down towards west. What you need not to confuse with, You should not consider this as south, and you need not to say from south to west. That will become wrong because that's a three-dimensional, right? So that's a very basic example, and this is given to us. This was given to us. We have simply handled the two together, and we are able to say what is the velocity of rain as observed by the running man. Answer is 5 meters per second, and at angle 53 degree from vertically down towards west. Make sense? Okay. So let's have one more example. What you can do, you can read the question, pause the video, solve it, and then check the solution that I'm going to provide now over there. So it says rain is falling with velocity 6 meters per second. So velocity of rain is given to us, and this is now at an angle 30 degree from the vertical towards north due to wind. So because of it, they are deviated. So it says find the velocity and direction with which a man has to run in order to see the rain vertically down. So what is given to us this time? Velocity of rain is given to us. Velocity of man has been asked. And what is given to us? Observed direction, that is vertically downside. So first of all, we will be having these directions. We will mention those directions. So we will say this is a vertically upward direction, and then this is a vertically downward direction. So this is up, this is down. When we make up down, then that means in horizontal direction rest of them is going to come, and we are interested on north. So better is that we can consider this is the north direction, and if we consider this as a north, so definitely this will become south. Can you see the way I'm drawing this direction, these directions over here? Then you will need, sometime you might also need need for this east and west. Then you can clearly say this direction that is outward coming is the east, and that inside going is the west. So here our focus is on north. So we need to show north so that we can have a nice diagram and geometry, and we can use the mathematics needed for it, right? So this is how we will be considering direction for this particular case. Now using these directions we can draw the direction, and the magnitude is given to us, and we need to draw the direction of velocity of rain. So velocity of rain is making some sort of this angle this time. So this is the velocity of rain, so that this angle is 30 degree. Same thing I'm drawing separately, because you can draw a vector anywhere, it hardly matters, as long as you keep the magnitude and direction intact. So this is the velocity of rain, and which has a magnitude is equal to 6. So this magnitude is a 6 meters per second. One thing. And another thing is that resultant, where the resultant is going to go. So resultant has to come vertically downside. So I'm drawing the resultant in it itself. So resultant has to come like this. That means this must be the velocity of rain as per the man. This is what the given condition is. So where should the person run? Now we want to say that velocity of rain as seen by the man comes with this this way. That means for this we subtract the velocity of man out of velocity of rain, and resultant we got to know. So we know if the person is moving in this direction, so velocity has to be reversed, so it has to be given in this direction. And if this person is running in this direction, then velocity has to be given in this direction, right? Now this is a vector. We will get this as a resultant if another vector is in this direction, because if it is in this direction, so resultant will come somewhere there, right? So using those concepts of vector, we can say this another vector must come in this direction. That means velocity of man must come in this direction. If velocity of man has to come in that direction, so where the man has to run? Man has to run in the direction which is opposite to this. That means person has to run, this is a man, this has to run in the direction towards north. So from here we can say the velocity of man must be towards north, right? So if the person runs towards north, so this velocity tries to turn towards the person, so raindrops will be coming vertically downside. So from here we can determine the direction. Now we want this as a resultant. So how we can handle that? We can easily handle that. This is 30 degree. we can make the two component of velocity of rain, one in the horizontal direction, another in the vertical direction. So one component will come in this direction. This will become VR, velocity of rain, into sine theta. Sine theta means sine 30 degree. Another component will come in this direction, vertically downside, which is going to be VR into cos 30. Are you getting this? And we need to now simplify this two vectors and this vector to get this as a resultant. Now you see, if we are getting resultant in the vertically downside, that means these two components must cancel out each other. That means there should be no horizontal component. So from figure we can conclude that the velocity of man must be equal to velocity of rain into sine 30 degree. Now velocity of rain is given to us, that is 6 sine 30 degrees, a half. That means man must be running with a velocity 3 meters per second. So from here we got to know what the velocity of man is, and this must be towards north. So in order to achieve this particular condition, man must be running towards north with velocity 3 meters per second. That becomes our answer. And if suppose if the question goes beyond and it further asks velocity of rain as seen by the man, then you can say these two components has got cancelled out, and the velocity of rain as per the man, if this magnitude is needed, we can simply call it as a VR cos 30 degree. Now we know the VR, we know the cos 30, we can also find the resultant velocity of rain as per the man. Making sense? So ultimately it's two vectors and their resultant by operation subtraction. So that can be performed. Now in application of relative motion, there is another type of problems. They are called river boat problems or river and swimmer problems. So here how we are going to handle the situations, we are going to talk about. So certain velocities will be involved over here. So we will be writing VR. So if we are writing VR, that means we are basically talking about velocity of river. Or we can also write VW, W for water. So velocity of water you say, or velocity of river you say. When we say velocity of river, that means basically the water flowing, right? And so let's say we are using this term W, or maybe river. Choice is yours. So I'm changing now and coming towards river. So that's the velocity of river or river water. With respect to what? I'm not writing another subscript, that means it's with respect to ground. That means if you are on the bank of a river and you just watch the water flowing, so that whatever the velocity you are going to get, that's going to be the velocity of river with respect to ground. And there is going to be another term that's called velocity of, we will write it as B, R. B for boat, R for river. You can also write S for swimmer if the person is swimming, and R for river, or you can write S W, or you can write BW, choice is yours. But point is, somebody who wants to swim or float or rowing on this river, and another is going to be river or water. So notations can vary, but yes, meaning remain the same. So this is going to be velocity of boat, B for boat, and this is with respect to river. So this is also going to given to us. So we will be given this, in this case these two velocities will be given to us. Our focus will be to find what the velocity of boat is. So when we say velocity of boat, that means it's a velocity of boat with respect to ground. This we need to find out. And once we are able to find this velocity of boat with respect to ground, then we can easily say how a boat is moving as per the person looking from the ground. So these are the three terms, and we know how to relate these three terms. These three terms can be related like this. Velocity of boat with respect to river is velocity of boat minus velocity of river. That's a formula. Since our interest in this case is going to be velocity of boat or velocity of swimmer or velocity of man, whatever you call it, this is going to be equal to velocity of boat with respect to river plus velocity of river. Now this case is going to be quite easier, because in this case you are going to add the two vectors directly, and you are not going to subtract them. So if you need to find the velocity of boat with respect to ground, you just write the velocity of boat with respect to river, and velocity of river itself, use the vectors, norms, and add them up together. You will find the velocity of boat in nutshell. Okay. And sometimes language will be a bit in different manner for particularly this thing. So this is basically velocity of river. This is velocity of boat in the river, that is with respect to river. So it will be also called as the velocity of boat in the river, or it can also be called as, that's the important point, velocity of boat in still water. So whenever it called in still water, that means it is with respect to water, because whenever we take a frame of reference, that frame of reference becomes still. Like earth for us becomes still even though it's moving. So that's the earth frame of reference. So whenever it says in still water, it means that this is velocity with respect to river, that means water. It doesn't mean it is with respect to ground. That might come in your mind. So a language will be velocity of boat or a swimmer in still water is this. That means basically we are being given this number. And if this number is given to us and velocity of river is given to us, we can easily find out what is the velocity of boat or the man or swimmer is by using this relation. Right. Now, these two velocities will be given to us, and then vector has to be operated for. And let's try to draw some figure that represent the river and the situation, because whenever the question will arise, it will always be good for us to draw a picture. So let's say we are drawing a top view of a river segment. So if you look the river from top, maybe from helicopter or somewhere, then it will be this one bank, this another bank. This is ground, this is water, this is again ground. And let's say we will show that the river is flowing like this. So this is velocity of river, this is VR. Unless a person wants to cross it by a boat, or a boat wants to cross it, and this is the A point where this boat is, and another point which is directly opposite to this A is another point called B. So B is just opposite to A point on the another end or shore. Now, if you have crossed a river by a boat, you might have observed, and if you haven't, take this observation whenever you get this opportunity. And if you are taking a boat and crossing this river, right? So, and you just want to go from A to B, just opposite direction, then you must have observed, or will be observing, that the boat will start moving like this. And it will appear to you that the boat is taking you somewhere else. But ultimately you will find you will reach to B instead of this point C. Why? Because of this rule. Because whatever this starts with is the velocity of boat with respect to river. And river adds its own velocity with it. And adding this velocity gives the proper velocity of boat. So this velocity is being added by this velocity, and hence you get the velocity in this direction. So boat will appear moving some portion like this, but actually it will reach over here. So this is basically let me write there, this velocity, if you are starting in this direction, so that's going to be velocity of boat as seen by the river or with respect to river, and this is the velocity of river. So we need to add this vector or this vector with this vector to get our answer, and we know this vector can be added up. So this becomes the final vector. So the person moves here or the boat moves there. Anyway, how we are going to solve this question? So I'm going to describe over here. This is our reference line. So we will take this vertical or this shortest distance as a reference line. This is a river view, river top view. And in this river top view, this is width of the river that has to be crossed. So let's say width of the river is D. and a person or boat starts sailing in this direction. That direction will be measuring by angle theta. So we are measuring theta from the vertical reference direction. Sometime in question it can also say that theta is from the direction of river flow. So that will that question will mean this angle as whatever the angle it is being said. But for us, theta is from this vertically referenced direction, and this is VBR. So that means boat starts sailing in the direction theta from this vertical direction, and we need to add these two vectors. So addition, we know we can add any number of vectors by doing their components, right? So this VBR will have a two component. One component will be in the vertical up direction, another component will be in this direction. So we'll make the two components, and this vertically up direction will become VBR cos theta, and this horizontal component will become VBR sin theta. BR is simply subscript and sin theta is getting multiplied. So we got to know this vector component and this component of that vector, and this VR is already in this horizontal direction. Here we are using a coordinate system, and that coordinate system we are considering it as origin, or the coordinate system that we are using, this as x direction and this as y direction. So let me draw over here. This is our x direction and this is our y direction. So we can say total velocity in x direction will be this component and this component together. Total velocity in y direction will be this component. Making sense? So this is how we are going to make the components. Once we have made these components, then we can use them to find our velocity of boat, which is a purpose. So we can say that this motion can be considered as a two-dimensional motion, and in this 2D motion we can have components along the x direction and y direction. So we will be describing the motion of x component. So if we work for this x component, we find what is the velocity in x direction is. Velocity in x direction, net velocity of boat in x direction. We are finally talking about the velocity of boat now. So that velocity of boat will have a component in x direction as VR, which is in the positive direction, minus VB comma R into sin theta. So that's velocity is in the x direction. Alright. And what will be the y component of this motion? So we will say y component of this motion is going to have a velocity Vy, and this Vy is going to be simply VBR, that means boat with respect to river, into cos theta. Now you see, this velocity, that's x component, will be responsible for x component of motion, y component of velocity will be responsible for y component of motion. And this velocity of boat and velocity of river, they are constant. That means there is no acceleration until and unless the question says that river flows with acceleration or boat starts with acceleration. That will be the question probably in the advanced level. So in most of the cases, if they say the velocity of river or they say the velocity of boat with respect to river, we say that they are constant velocities. So since the velocities are constant, so there is no acceleration. So this description of motion is quite easy. This is Vx, this is Vy. So at any instant of time, how much the displacement will be in the x direction, we will say it's a simply Vx into t. So displacement in the x direction will be given by this equation. What will be the displacement in the y direction? So let's say displacement in the y direction is y, and so that's going to be velocity in the y direction into t. So they will give us displacement in x direction and y direction. And if we want to know what the time taking to cross the river is, what the x coordinate is going to be, all that we can easily find out. How we can find out? Total displacement in the y direction is going to be d. So we can replace this y by d. So that becomes d, and this is known to us. If this is known to us, from here we can calculate the t value. Then we can substitute the t value over here. We can find what the x is. what the x is. That means if the particle lands finally, or the boat reaches over here, you might have seen, or you may be having this kind of experience, that if you target to B, you might reach to some point C. So if it is reaching to C point, that means this is the displacement in the x direction that has taken place. So this x is basically whatever we are writing over here. How we can calculate this x? We need to simply put the t which we have got out of it. Now this t is going to be the time taken to cross the river, because generally we will not be interested on those points inside the river. Rather, we will be interested on the points that when the boat reaches to other side. Okay, so this x is called drift. So in the language of this x is known as drift. So river drifts boat by what amount? So that is the distance traveled along the direction of river flow. That's called drift. So now we will be making formulas for drift calculation and for time calculation, and then some more frequently asked formulas. Okay, so this slide tells us about river boat problems. Let me quickly re-explain. This is river velocity, this is critical point, it's also called still water velocity, and then this is what something we need to find. This is addition of two vectors. How we are adding two vectors to this theta we are assuming from the vertical, making two components, and this is another component that we are adding up. So x component velocity is this, and y component of velocity is this. And then from here we can find the drift, we can find the time taken to cross the river. Okay. So in the same situation, these are the equations. Now let's try to find some important quantities like time to cross the river. So if someone wants to find the time to cross the river, how much time it will be taking to cross the river, so we can use this equation. And here we know this displacement in the vertical direction is going to be d, so we can replace this y by d, so it becomes d is equal to vy into t. So what the time comes out to be, so time to cross the river is simply d divided by velocity in the vertical direction. Now which is the velocity in the vertical direction? This is the velocity in the vertical direction. So from here we got a formula. Time to cross the river is the width of the river divided by velocity of boat in the river into cos theta. So that is important formula, and simple as well, and that has to be remembered. And how to use it? Theta will be given to you, VBR will be given to you, D will be given to you. We can find what the time it will take to cross the river. And of course we need to put the D and VBR in the same unit system, or probably SI unit system. Theta will be given to us, right? Or theta will be used to find out other things as well. So this is the time to cross the river. But generally it asks what should be the value of theta, what should be the value of theta, so that time taken is minimum, because this is one of the purpose of persons crossing the river, that they would like to have like to cross this river as quickly as possible, because every time things are faster, so they want it to be done quickly. So what is the t minimum, what is the minimum time, and at what angle one should start sailing their boat so that the time taken is the minimum? So we can say from here minimum time, t minimum. Now how this is expression of t, from here we can mathematically find what the t minimum is going to be. It's a d, we cannot change the d. That means river width cannot be changed. And if you have started with that means boat has a particular velocity, so that can also not be changed. So if boat has a particular velocity, so what should be the theta? So can we say cos theta should become such that, so that this t becomes minimum, and we know this is in denominator, so it becomes maximum, and in cos theta maximum is a 1. So you'll find whatever I have written, that's formula for t minimum. So if sometimes equation asks what is the value of minimum time to cross the river, this is the minimum time. That means you divide the velocity of boat with respect to river by the width, you can get the minimum time. And also you can find at what angle one should start sailing the boat. So this will happen when cos theta is 1. That means what? theta is 0 degree. So if you start at 0 degree, then you will be crossing the river in the smallest time, that means quickest. And theta 0, what does mean by theta 0? If I redraw this picture that we have used, so if you want minimum time, then in which direction you start? You need to start in the direction which is perpendicular to the river flow. So if you want to cross from A, and so you must start in this direction. If you start in this direction, so this is your VBR, theta now is 0. Of course, you are not going to reach at the point B. You will be reaching at point C. That's a different story. That means you will carry some drift, but you will be reaching another end, or from this side to this side, in a shortest possible time. So that's the minimum time. For minimum time, theta is to 0. That means you need to start moving in the direction just opposite. But because of the river velocity is going to add it up, so it will be reaching to C point, but it will be fastest. So river is moving in this direction. Makes sense? So this question has been asked in the examination many times. At what angle should we be starting and what is the minimum time? You can easily find out. After calculation of time and minimum time, another point is calculation of drift. So we have already talked about this, how we can calculate this drift. Drift is first of all, it's a definition. It is the displacement along the direction of a river flow by the boat that we are having. That means it's basically x value. And how we get this x value? X value is Vx, which is given to us, into t. T we have already calculated. So Vr minus Vb comma r into sine theta, and into this is this, and into t came out to be d divided by VBR into cos theta. So that becomes the formula for drift. So if you have been given the width of the river, theta angle in which you are moving, and these velocities, this expression will let us know what the drift is going to be. So you can easily find out. But in the questions, most likely you will be asked about this minimum drift. If you want minimum drift, so what is the minimum drift and at what angle that will be achievable? That means you want that if you start from A point, you reach to B point, or at least minimum distance from the B point, not farther apart, right? So that means x has to be as least as possible. So we want x to be minimum. You can minimize this expression which we have written for this x, and this is theta is a variable, so with respect to theta you can differentiate and do the stuff, and you can find that thing. Anyway, so this x minimum will have two cases. So case 1, let me write directly. Case 1, there will be two cases. Now this x minimum can be 0. So x minimum can be 0. So minimum drift is 0. That means person starts from A and reaches to B. So sometime question will ask what the boat should be doing, or in which angle boat should start moving so that it moves just opposite to the point it started with. That means it reaches to B. That means we need to make this x 0, and x is a drift. So minimum drift is 0. X is going to be 0 or more than 0, right? Because we are talking about the magnitude. Even if it is in this direction, so that will be counted as a magnitude. So the minimum value of x can be in absolute term, that is going to be 0. And if you want it to be 0, of course time is non-zero. Time, it will take certain time to cross it. So what we need to make this Vx to be 0. So this 0 means Vx has to be 0. Can Vx become 0? Yes, because there are two velocities and they may get cancelled out each other. So this can be 0, that means this term must be 0. And if you make this term 0, then you will find this Vr should be equal to VBR cos theta, that is sin theta. From here you will find what the sin theta is. Sin theta is going to be equal to velocity of river divided by velocity of boat in the river. Making sense? So from here you got a very important formula that called to find the angle theta with which the boat has to start or move so that it causes minimum drift, that means it reaches just opposite end. And it is coming VR, which is given to us, VBR, which is given to us. Just take the ratio and that becomes sin theta. So theta is equal to sin inverse this number. Now, this will not be true for all the values of theta. This will be true for those values of VR and VBR, so that theta is defined, right? Because we know sin theta is always less than or equal to 1. So that means this will be valid. So this is valid if the condition is this VR, the velocity of river, should be less as compared to the velocity of boat in the river. So that means river velocity should be smaller and boat velocity should be larger. Then you can apply this expression. If it happened to be otherwise, it won't work. It won't work. There is a limiting case as well. I am just rejecting the limiting case as of now. We can consider it separately. So this will be valid when this number is less than 1, right? And otherwise this won't be true. So this is for the case 1. The case 1 will be valid when this is the condition. Now, what the case 2 is going to be when this condition is not met, then what is going to happen? So that's called case 2. Case 2. So we can directly say this case 2 is basically the case if velocity of river is greater than velocity of boat in the river. That means you think practically, river is faster. River is moving faster as compared to the boat. So river definitely take this boat drifted towards its direction. So you will never be able to reach this B point. You will be going drifted with the river because the river is furious, it is faster. Okay, so this is another case. In this case, we cannot claim this x minimum is going to be 0, so x minimum is going to be a number, right? And how to get that x minimum? Now you got to know this, then we will need to use those formula. That means we will differentiate it, put it 0 to get the minimum value. So this is the case. Then what we need to do? You need to do dx by d theta, so and put it 0. So this is, I'm leaving to you as a homework, and you can do that. You just differentiate it with respect to theta, treat all other as a constant, and then put it to 0 because you have learned what is the differentiation is. And once you do this, then you, after calculations, you will get this as a result. What you are going to get as a result, that I'm going to tell you or share with you. So when you do this differentiation, put it 0, that means we are basically interested in minimizing this x minimum. So we are interested in x minimum, that means minimum drift. We are talking about the minimum drift in this case as well, right? So after doing this, you will find, you will get some sort of this. Sin theta is equal to VBR divided by VR. So this is what you need to verify after doing the differentiation, putting 0 in order to get this x minimum. And to remember, it's quite simple. Whatever this was, since now VBR becomes smaller, so this ratio becomes reciprocal or reversed. So this is how this calculation goes on. So that's a part of homework. You just prove that you are going to get this. And sin theta is VBR upon VR. If you get it, that means you have done the calculations correctly. Anyway, so from here we will be knowing what the angle in which direction the boat must start with, so that it causes minimum drift. It's not reaching to opposite end, but whatever the x is going to be, that will be minimum. Then the question can also be, what is the minimum x? So how we going to get this x minimum? In this expression, we are going to put the theta the theta we have calculated from here. So x minimum will be calculated using above theta, whatever the theta that we calculated, using above theta in x formula or drift formula. So drift formula is written in the top. In this drift formula, we place this theta, we will get our x minimum. So this x minimum will not be 0, whereas this x minimum is 0. So x minimum will be achieved if river is flowing slower than the boat, and if the boat is flowing slower than the river, then the drift will be non-zero and can be calculated by this theta and putting this theta back on this. So I hope you got to know what the methodology is and how this is coming. So complete this homework and then this gets completed. So questions are going to come directly. You can use this formula and this formula directly. Remembering is quite simple. Okay. And at the end there is a question, so you just go through this question and I'll give these two answers in the comment section below, and use the concept that we have just learned, right? So this is all about this video. In this particular video lecture, we have covered a lot more important aspects related to the rollator motion. So just make your notes properly, and if there's any doubt, you can ask. Thank you for watching. Have a great time.